Okay, we're going to get started again, and we're getting to the question and comment period. But I first thought I'd just give a very brief sort of overview of what Claire has presented, if I can. It's a lot of material there. Again, this is geochemical characterization in order to try to predict as well as possible how much acid is going to be produced from waste and tailings materials and how much metals would be released from these. That's a very hard thing to do, to predict that. And she's a series of, I'd like to point out that even though standard tests are used by most industries, this is not like something that's been tested over and over, and we know the approach, and it's a clear path to how to get to the goal that we're going to. There's a lot of uncertainty involved. I challenged somebody one time with showing me a published peer-reviewed paper that actually has done the standard tests and then been able to predict within a reasonable reliability that that's what they got in the field. And I don't think there is such a paper yet, but I think we're getting closer to such a situation. And what the non-standard test doesn't mean that these are any less reliable, doesn't mean they're any less useful. I would consider them myself to be more useful because they are the first attempt to go beyond the simple lab test and try to do a small scaled up field test that gets a little closer to realistic conditions. So she explained static and kinetic tests, the tests that they've done, sort of standard protocols, and she went through some non-standard protocols, which I think were getting us closer to more realistic conditions, and including the barrel test, obviously. And at each time there's another test, she's trying to quantify the release rates, usually in terms of sulfate, but this is also acidity and copper concentrations. Trying to quantify that, again, a very hard thing to do, and compare each kind of test as she goes to more and more tests that are hopefully getting more realistic, including checking against aging of cores, which I don't recall having heard anybody actually done before, which I think is a good idea. You've got cores sitting around at different ages, exposed to air and water over different time periods, and then you can analyze those leachates and see how they compare with the standard tests. Also, subaqueous tests are important because this is one of the ways in which we can keep sulfide materials from oxidizing and creating acid is by keeping them underwater in anoxic conditions. So that's a valuable thing as well. And trying to quantify weathering rates and comparing them is again getting us down that path that we want to be towards, how acid producing is this stuff. And then the goal, of course, is to, once we think we have a good handle on that, figure out what mitigation we need to build into the whole mine plan operation. Okay, and there'll be a chance for more questions on all of this. At this point, we have one of our panel members who's going to give his critique, and I'll let Phil introduce him.
So we'll have this is the opportunity for the panelists to interact with the consultant who did the work. And we gave our panelists different assignments on different chapters, and also they had the opportunity to put together a presentation or a couple of slides to help direct discussion. And Dr. Tom Al, who we introduced in detail yesterday, is our geochemist on the panel. And he's a professor at the Department of Earth Sciences at the University of New Brunswick, and has worked on geochemical and hydrologic studies of mine tailings and waste rock and the release of constituents to groundwater. So he's going to come up and give a short overview of his critique. We thought it'd be important for Claire to be able to potentially respond while he's going over his critique, so she's at the microphone at the end of the table. And so when he's done, the rest of the panelists will come up and continue the discussion. And after that, it'll be followed by the public discussion period. So, Dr. Tom Al.
Thanks, Phil. Okay, I first want to figure out how things work here. Can I point at all with anything here? Is that it?
Yes, that's it.
Okay, good. Okay, so I'll just go through, as Phil said, a few slides. Claire, at any time, or if you want to jump in and have something to say about what I'm talking about, that's fine. So just first a basic summary of what has been done. Most methods, certainly some of the methods are industry standard, as Kirk said. Others have been modified, showing some tendency towards innovation, and that's all good. Industry standard, I'm not meaning to imply that that's always great and it always gets us to the end that we need to get to. It's, the industry has been evolving over the years and we're getting better, but, there's still lots of things that need to be learned to be able to do a better job. I would say the data are of high quality. They've done a very good job in collecting samples, analyzing samples, compiling data, presenting the data. These data, as Claire mentioned in much more detail, can be used to investigate the potential for low-quality drainage, and that's mostly what I'll focus on, this business of acid drainage. I'm not going to get into too much, copper concentrations, molybdenum concentrations. Claire mentioned the dependence on pH, and that's very important. So if the pH drops, I think we know that the copper concentrations are going to go up. But pH isn't everything, as Claire said as well. Selenium, molybdenum, arsenic, they're not necessarily pH dependent at all. Or not. We don't require low pH in order to see them come from the waste. Okay, so in terms of the work that's been done, it generally falls into this category of prediction, and I guess I want to talk a little bit about prediction and how good we are at prediction as scientists. To do that prediction, there's two basic methods used. Claire talked about static tests, which often are referred to as acid-base accounting. It's, I would say, a useful approach, and here's where standard methods have been employed, and that's all good. It's fairly easy, I would say, to interpret these data when they fall in certain ranges, and I'll show a slide next, and Claire has shown slides similar. When they fall to one end or the other, say into the potentially acid-generating range or the non-acid-generating range, then it becomes pretty clear that we either have a problem or we don't. There's more uncertainty, of course, as you approach this one-to-one line where the acid potential equals the neutralization potential, and there's this often termed the gray zone around that line. So one of the issues is, how do we define that gray zone, that zone of uncertainty? Okay, so what about the Pebble data? Here, what I'm showing is not complete data sets. On the left slide here, the data for the pre-tertiary rock, the mineralized rock, are shown. And the same thing on the right slide, it's the pre-tertiary or mineralized rock from the east zone. So the tertiary rocks are not represented here. And if you recall the data that Claire showed, if, for example, we look at this one, the tertiary rocks would mostly fall in this, hopefully it's showing up as pale green in the upper left. But the pre-tertiary rocks, the mineralized rocks, really fall a few within the uncertain zone defined in blue or in the potentially acid-generating zone. So these mineralized rocks and the waste rock associated with them are essentially acid-generating. And they fall, I would say, far enough within that zone to be confident that there will be acid-generating properties here. Okay, there was work done on the tailings, and here is the presentation of that work. Claire also showed this. I've just put the colors on to help differentiate the different fields. So in these particular analyses, these tailings are what they call low sulfur tailings. The ore has been removed, so a lot of the copper sulfides are taken out, and also they've removed a pyrite concentrate, and that's important to recognize. So So these are low sulfur tailings because a lot of the pyrite's been removed because it's associated with gold, and also the ore or the metal sulfides of interest like chalcopyrite have been removed as well. But still, some of those samples fall within the potentially acid generating range. Okay, so back to prediction. Static tests or the acid-base accounting are one way of predicting, but that prediction has no timeline associated with it. So the prediction says, will they or will they not generate acid? And there's nothing about time in that prediction. But when we get to kinetic tests, by definition, kinetic relates to time. So kinetic tests are an attempt to put a time scale on some of these weathering rates, processes, and they use things like humidity cells and aqueous submerged columns, aerated columns, etc., to get some handle on these oxidation rates. So these are done primarily in the lab, but as Claire showed, there's barrel tests that have been done at this site, and at some mine sites they set up test piles and monitor those, and that's all quite useful. But there's some very, very important points to make here. And first off, the lab cannot replicate field conditions, right? So we can take these samples and we can take them into the lab, and we can try to make predictions of sulfide oxidation rates and look at sulfate release rates, and all these parameters of interest are studied. But in the end, we cannot replicate field conditions. So things like complicated drainage flow paths. When you build these waste rock piles, they're notorious. Hydrogeologists trying to understand these waste rock systems are always confounded by this problem. We just don't know where the water's going. Right? It's very, very heterogeneous. There's problems in material mixtures. These piles are not homogeneous in terms of their sulfide content and their neutralization potential and acid potential content. These are very heterogeneous materials just because the mining process goes through different types of materials, and those materials end up on the dumps at different times. Climate variability, okay, seasonal, long-term, all sorts of changes in climate lead to changes in rainfall, temperature, and so on. And all those things add a lot of uncertainty when we try and think about taking the results of these lab tests and as Claire said, scaling up. So scaling is necessary if you're going to use these types of results to understand things like the timing of onset of sulfide oxidation and acidification, or if you're going to try and predict water quality. Okay, again, that type of prediction involves time. We know what the water quality is today, perhaps, but if we want to predict what it's going to be like 5 years from now, 10 years from now, 100 years from now, there's a lot of uncertainty associated with those predictions that involve time. Okay, so I would say it's not possible. I'm making a very emphatic statement here, and Claire might want to refute this, but I'm saying it's not possible to relate lab results to actual behavior of the waste in the field. Okay, that's flat out. I think, personally, that that's a very, very difficult thing, and it's fraught with uncertainty, and we should be very careful if we're going to even go through the exercise of making predictions. We really have to put bounds of uncertainty on that, and it's also a very difficult thing to do. Okay, so here we are. If the aim is to predict the timing of acidic drainage and specifics of water quality, then these kinetic tests, I would say, have very little predictive value. Okay. Now, that has been done. Okay, so, and that's being presented. So this equation was shown earlier, this timing of onset. There's an equation here, and we can talk about the release rate and the effective NP and the critical NPR ratio and so on. All these terms can be defined and can be extracted from, let's say in this case, from the humidity cell test, and they can be put into an equation and we can get a result. But the real issue is, what is our confidence in that result? So confidence in a situation like this comes from repeated successes in prediction. So if we had a record in the mining industry of doing this over and over and over again, and there was success into the, as time goes on, each time, okay, we got it this time, we got it next time, and we get this sequence of prediction and successful matching with prediction from the field results, well, then we would have confidence in this prediction process. But I would say that at this stage, with the state of the art, we don't have that kind of confidence. Okay, we don't have that ability to predict with confidence. So this sort of exercise, we can go through it, but I would say it shouldn't lead us to statements like the one shown here. Okay, so I can't read it very well there, and I can't even see it without my glasses here. So the calculations are consistent for laboratory and field conditions and confirm, very strong language, confirm that the time frame of acid rock drainage generation under site conditions is at least a decade to several decades for fully oxygenated pre-tertiary rock. I think we have to be more cautious in our predictions. I don't think that's the sort of language that we need that's going to take us forward and help us work towards design of site infrastructure and mine planning. So predictions of timing are very uncertain, and they should not be used, I think, for management decisions. Okay, predictions of drainage water quality might be better, and we're talking specifically about drainage water quality, might be better, and I was really glad to see Claire talking about analogs. There's a lot of information on deposits of this type elsewhere in the world, and they weren't necessarily managed as well as they should have been, so perhaps conditions are not as good as we'd like to see at some of those sites, but we can learn from them. We can and should learn from them. And analogs from other mine sites can provide, I think, a lot of information about what drainage water quality might be under specific conditions. So I think that's a great thing to do. And
can I just ask, Steve, my colleague Steve Day actually prepared a sort of draft white paper on exactly that subject, the kind of the data from analogous porphyry deposits and the experiences in other mine sites. And I believe that paper was submitted to the Keystone panel for your review. Have you seen it?
I haven't.
Okay. Well,
No. I'd like to, though.
Yeah. Well, we should make sure that you get to look at that.
Okay, great. Okay, so then just to summarize, we bring the rest of the panel in. From the waste rock point of view, I'd say there's little uncertainty with respect to pre-tertiary waste rock. Under exposed conditions, much of the material, I would say, is likely to generate acid drainage, and I think that's a conclusion that's general, comes from SRK as well. Here's I think one of the most important issues here when we talk about prediction and why we do it and how we use it. Management of waste rock commonly involves segregation of the non-acid generating material from the acid generating material. And for example, that segregation could be required. I have no idea what the plans are here, but it could be required to do something like building tailings dams. So you need rock for constructing these dams. If they could segregate non-acid generating waste rock, use that non-acid generating material to build the tailings dam, that's advantageous. The transport distances, costs are probably lower, and so on. But it's very, very important that it's segregated properly and that the material that's taken out as non-acid generating never does generate acid. So it's very important how these decisions are made for these segregation purposes, and I think we have to be very careful then in getting it right. So this identification is a significant challenge. Particularly, we've seen the pre-tertiary material is dominantly potentially acid generating. The tertiary material, not so much. There's some that is, but not very much by the looks of it. So it seems like it should be fairly easy to get tertiary rock that you could use for construction activities. But issues like using an NPR of 1.6, so that comes from the release rates from the humidity cells, I believe, right?
That's correct,
That's
yes.
where that number comes from. So I think taking that number, it's less than what might be a standard number. So a standard number of 2, 3, sometimes even 4 would be used. I think MEND uses 3. Is it?
MEND uses 3, yes.
Right, right. So to go down to 1.6, I think, based on humidity cell tests, which I don't have a lot of confidence in, seems a little bit risky. Oh, neutralization potential ratio.
That was the NP over AP ratios that I was referring to. I acknowledge that I guess what we need to do is some sensitivity analysis in terms of use of this factor as a decision criteria. I think in general terms, all the pre-tertiary waste is likely to be treated as if it's PAG, irrespective of what that ratio is. It'll probably become a little bit more critical when we're looking at the tertiary material. Now, the majority of that material we believe's NAG, as you call it, but we do know that there's a proportion of it that might be PAG, and I think it's important that we try and differentiate that volume of tertiary material from the rest of the tertiary material and manage it appropriately. And I guess the use of this ratio might not, there are various ways we can use it, and one way would be to try and incorporate it in some way into the mine model, into the geological block model. As I mentioned in my presentation, we've used the total sulfur content in the drilling program as a kind of indicator of sulfide content. We've also explored the use of calcium as an indicator of NP. If we combine those two, we can actually calculate a surrogate NPR value and introduce that into the block model. But we need to define, if you like, a flag value to categorize the material as one type or the other, so that we can have a look at how that material might fall out of the mine schedule and whether it's actually operationally possible to segregate, particular blocks within particular units of material. So, it's a criteria, but how it's going to be used goes beyond just deciding whether it's PAG or non-PAG. It's kind of a tool, if you like.
Yeah.
But yet, you're right, we should certainly do some sensitivity around, changing that value and what implications that might have.
Yeah, the precautionary principle would just say, if 3 or 2 is the number that's used generally, then we need to have good reason to lower it, right?
Yeah,
So,
you're probably right there, yeah.
But I agree with you, if you use calcium analyses and sulfur analyses, for example, in a program that's almost analogous, mining companies segregate materials all the time. That's how grade control operations work, right? You go in and say, well, this is ore and this is waste, and that's done routinely, but it requires a very detailed analytical program and day-to-day kind of being on top of sampling and whatnot. So if you could use calcium and sulfur in a program maybe analogous to grade control, then this sort of segregation, you start to get some confidence in that sort of approach. So, okay, so I think this is my last slide. Tailings, I wanted to make a few comments about tailings. It's actually, there's not really enough information to think about tailings at any great depth. So that's why I say it's a little more complicated. The acid-base accounting results from the low sulfur tailings are close to the zone of uncertainty, but these are just the low sulfur tailings. They don't include that, whatever the pyrite concentrate fraction is. It's not clear to me how much pyrite concentrate there would be, but they have to dispose of that somewhere, and that's not talked about and not really discussed. So if it was co-disposed with these tailings, that's going to push these perhaps out of the range of uncertainty down into the potentially acid-generating range. And so these are the sort of issues that we really don't know enough about because we don't have a mine plan, and we can't really talk about it too much. There's a small number of samples for the same reasons. Okay, so the last point here is really just about the pyrite concentrate. The reason they would generate a pyrite concentrate is so they can recover gold. Gold is intimately associated with the pyrite. So if they concentrate pyrite with flotation techniques, then they can somehow get the gold out of the pyrite. There's several ways of doing that, but none of those are addressed in the EBD, and therefore it's hard to evaluate how those processes could influence the geochemistry of the tailing system. So that's a gap in knowledge at this point. I'm sure it will be closed, but it's not something that we could really address at this point. So, okay, so that's all I have to say. Maybe you want to bring the panel up?
Yeah, I think that's what So at this point, we'll have the full panel up here to ask questions for clarification. And it's the same members as we had yesterday, but we'll just do a brief introduction. On the far left is Dr. Jeremy Richards, Professor of Economic Geology at the University of Alberta. His expertise is he's the economic geologist on the panel and has worked on porphyry and gold systems for a number of years. Tom Al just gave his critique. Dr. Chris Way-Thomas is a research scientist with the USGS here in Anchorage in the Alaska Volcano Observatory, and he is a superficial geologist with expertise in geomorphology, hydrology, quaternary geology, and looks at hazards associated with volcanism in Alaska. Steve McNutt, professor at the University of South Florida, had spent nearly 21 years with the Geophysical Institute in Fairbanks, and his background is in he's a seismologist and working on seismicity associated with volcanoes and volcanic hazards with extensive experience here in Alaska. And then Dr. Larry Goff, who's an emeritus research botanist with the USGS in Reston, Virginia. His expertise in biogeochemistry, soil geochemistry, mineland reclamation, plant ecology. And he formerly was living in Anchorage and has worked for over 30 years in Alaska. So does a panelist have do you want to start with Jeremy? Do you want to work through this? Or I'm not sure how many questions we have here.
Sure, I can kick off.
And we need to make sure we speak into the microphone.
I guess what I would take away from this is that these wastes are going to become acid generating at some point. The equation that you provided for the time of onset, I didn't really understand that equation because it didn't seem that zero was a possible answer. It didn't seem that you could solve that equation for a situation where you never generate acid. It seemed it would tend to infinity, but it appeared that any type of combination ultimately is going to generate acid. So I didn't quite understand that equation. But from what I could see, the materials that are likely to go into the waste rock piles are sooner or later going to be acid generating. And as Tom mentioned, those piles are going to be very heterogeneous. So the likelihood is that for any given pile of waste material, it may start to become acid generating in one part quite early, and then other parts might be later. But I would imagine that acid is going to be generated out of those piles from almost day one. Would that be a reasonable thing to say?
Oh, can I just qualify the like waste rock that's sourced from the pre-tertiary mineralized material? I think we can assume that it's going to go acid at some point in time. Waste rock that's sourced from the tertiary overburden is classed as non-PAG,
Right.
and we wouldn't expect it to go acid.
Mm-hmm.
So, and actually, in terms of the volumes of tonnage to be managed, it's possible that the tertiary might dominate the overall tonnage. So I think that's an important point. Although, until there's a mine plan and a mine schedule, we can't actually put numbers on that.
Right. But I think, from the point of view of thinking about this mine in the long term, it's inevitable that there's going to be acid-generating waste materials produced at some point.
Yes, certainly from that pre-tertiary zone. And the question is, how are those materials going to be managed? Are there containment options, engineering options that can be put into place to ensure that any products of that acid onset are contained or treated before release to the wider environment?
And that would be my question to you, are there?
There are options available. I don't know what options are being considered for this particular site.
But potentially there's an engineering solution to this challenge?
There are potentially solutions. There are ways that you can construct waste rock dumps to try and control and minimise gas transport within the dump. For instance, just to pick one particular control on oxidation rates. I mean, clearly, the oxidation rate for the sulfide to oxidize, it needs access to oxygen. If you sort of imagine a really big waste rock dump. At the time, if you imagined that waste rock dump was constructed instantaneously and was immediately a huge dump, at time zero, oxygen would be available throughout the pore space of that dump. But as that oxygen is consumed in the kind of interior parts of that waste rock dump, it needs to be replaced and before further reaction can take place. And that then becomes a scenario where the whole thing's limited by oxygen supply rates from the external surface of the dump. So you can construct dumps to minimize the permeability of the dump to air transport, and you can also cover dumps with materials that have very low permeabilities, and both those solutions can contribute towards minimizing or controlling oxidation rates.
Okay, thanks.
Claire, I just really have one question here, and it relates to something that was in your presentation. It surprised me a little bit. You talked about subaqueous storage of waste rock, and this kind of relates to what you were just talking about in designing dumps for oxygen transport limitation and so on. Is that a potentially viable option given the volume of material here?
I don't know how viable it might be viable if there was a small volume of particularly reactive waste. Perhaps there's some form of containment where you could envisage there being a permanent pond of water that you could submerge the waste rock within. And if that were possible, certainly submerging the waste rock so that it is covered with water limits the supply of oxygen to that waste material very considerably. Water contains oxygen. Oxygen can be dissolved in water, but the maximum concentration of oxygen in water is much, much lower than the concentration of oxygen in air, which is 20%. So, we're talking about a reduction of orders of magnitude in the oxygen concentration. So those are options, but how viable they are in the context of this project, I don't know the answer to that.
I'd like to actually just remind the panelists that we have a wide range in background in the audience and on the through the web seminar. So let's make sure we keep terminology fairly straightforward, or maybe rephrase things periodically, just so it's clear to as many people as possible. Thanks.
I have a couple of questions too, Claire. Since subaqueous was mentioned here, I'll just remind everybody that this is Alaska, and we have winter usually 6 months, and water quickly turns to ice. So subaqueous storage may be sub-ice storage for most of the year. But this issue of freeze-thaw comes to mind. We have parts of the fall and spring where the temperature hovers around 0 degrees, and freeze-thaw processes are particularly efficient at breaking up sediments. And I just wonder if you guys have entertained the effects of freeze-thaw on how these reactions might be affected, and what could be done about that.
Well, temperature is an important variable in terms of the oxidation rate. And another thing that hasn't been mentioned yet is one of the things that catalyzes or encourages the sulfide to react is the presence of bacteria. And at very, very low temperatures, 0 or close to 0, I think the general feel is that bacteria don't like it very much, and they become dormant or ineffective, and that might actually cause reaction rates to decrease quite considerably. There is some work on in the Divik mine site, I don't know if you're aware of that site, where they have some big test piles of waste rock, and they're actually monitoring the behaviour of that waste rock as a function of freeze-thaw cycles. And some of the data there's quite interesting. Another thing we need to remember is that, and again, this hasn't been talked about, it's another level of complexity, I guess, is that the sulfide oxidation reaction is exothermic, which basically means it generates heat. So the reaction can actually cause local heating within the waste rock dump, and it might actually, in some cases, prevent freezing in some scenarios. So the distribution of temperature and the controls of temperature in the heap go beyond the climatic conditions. They actually are also a function of what's going on in terms of the reactions inside that waste rock pile. I'll just say another thing about the kind of logic behind the subaqueous column, as well as generating data that would be pertinent to use of that as an engineering solution for managing waste rock. We were also targeting that at other mine features, like, for instance, if an underground mining method was used and there were underground exposed faces that would, after mining had ceased, would be reflooded, then the subaqueous column data starts to become pertinent in that scenario as well.
Just a couple of other minor questions here. Maybe you could comment on the representativeness of the samples that you used. How realistic are those as what you might expect to actually get out of the mine itself?
That's a difficult question in terms of whether we've covered the broad range of characteristics that are going to be encountered in mining. I would like to believe we have. In terms of whether our sample densities are statistically representative of the volumes of different materials that are going to be mined, I can't really answer that until such time as a mine plan's available and we can actually then compare our sample densities to the actual planned volumes of material that are going to be mined.
And so where did you get all that material? Is that from the cores
The
themselves?
The material that we've studied was from exploration cores,
Okay.
mostly diamond drill cores. And basically what we've done is tried to get a good spatial coverage, like both laterally and vertically, but how that spatial coverage actually relates to planned mine volumes, we can't assess at this point in time. I'd like to hope that it's not too far off, but clearly we'll have to refine the data set as we go forward.
Right. The last thing I just want to ask about is just what your perspective is on the long-term acid generation issues, considering longer time scales, like 100, 200, 500 years. Is there some kind of predictability associated with acid generation over time scales like that, or is it completely unknowable?
Well, okay. we are going to try and predict it, but I mean the point that Tom made earlier about there being uncertainties in this process and the fact that the large-scale waste facilities are complex makes it a very difficult thing to do. But we're going to have a go because you know you need to start somewhere. But clearly, whatever we predict would be used, if you like, to help form the monitoring regime. And as soon as monitoring data were to be collected that falls outside the bounds of what we've predicted, then we would have to iterate and adapt any predictive model that we developed accordingly. So, you know, we've got to start somewhere, and we will try, but there will be significant uncertainties, and what we will try and do is document, you know, where we believe the main uncertainties actually are, and try and do some kind of sensitivity analysis around those. And basically going through that kind of exercise allows you to prioritize data collection as well. So, you know, we'll be doing our best, but, you know, it's difficult.
That's all I have.
I have a question that's looking at some of the basic physics. I mean, one of the parameters as far as exposure and the rates of the various chemical processes would be the surface area that's exposed. So I presume there's some leeway in the design of the shape of the piles and the location to try to structure them in such a way to reduce the rates at which these processes occur.
Well, there's various physical aspects to that question, I guess. I mean, the waste rock pile will include a range of particle sizes from fine material that might be quite similar to the material that was in the laboratory tests to very, very coarse material like huge boulders, for instance. So clearly the particle size of the materials that are in the waste rock dump need to be considered when we're looking at reaction rates. But another aspect is the geometry of the waste rock pile, and that comes back to the point I made before about oxygen supply mechanisms. If you've got a very, very thin, shallow pile that covers a very large surface area, you've kind of maximized the external surface area of that pile. So the behavior of that particular kind of pile would differ from the behavior of a very tall pile, for instance. And all of those questions come back to the mine scheduling and how much tonnage, how much volume of waste is to be managed, and how that waste rock is to be scheduled, and how they plan to construct the waste rock piles. So there are questions related to the shape of the pile that we would have to try and incorporate in our kind of predictive exercise when we get to that stage.
And presumably all these reactions start on the outside of the pile and work their way inward. Is there sort of a core of the pile that never really changes, sort of inert?
Well, that will depend on a number of things. I mean, you also have to think about how quickly the pile is constructed. I mean, you know, usually they're constructed one lift at a time. So certainly before the second lift or the second layer is emplaced onto the lowest layer, then that material is exposed to reaction. But then as more and more subsequent layers are added, the deeper layers might consume the available oxygen and stop reacting and thereafter become inert. But then you also need to remember that if acid water were being generated higher up the pile, that water could then percolate downwards and might leach metals from the lower materials, even though those lower materials themselves are not oxidizing. So there are a number of quite complex processes that we would have to factor into a kind of conceptual model of how the waste rock heap is behaving.
Larry, do you have a...
Maybe this question would be better asked of Craig yesterday when he was giving the soils talk, but in dealing with the reclamation, the mine land reclamation that will you guys will be involved in, certainly. Is there consideration for segregating the sulfide minerals before reclamation, or has that even been considered yet?
You mean like processing the waste rock, if you like?
Yeah, and you know how you're going to be topsoiling and that sort of thing, and planting. I was just wondering if there's a segregation method that you'll be using for these sulfides before the reclamation takes place.
I think there will almost certainly be some form of segregation of reactive materials from non-reactive materials based on some criteria around the sulfide content of the material. In terms of, I think, are you really talking about whether the soil that's kind of scraped off before they mine, is that preserved, and would that be then replaced on top of a waste rock pile?
Right, and of course the depth of that cover soil is critical.
Yeah.
Based upon how much sulfides are in the waste rock that's being reclaimed.
Yes. If you had a heap of very sulfide-rich waste, yes, you'd need to consider if you're covering that with a soil. You're right, it would need to be fairly thick because there is the chance that acid leachates might impact on the health of that soil and impact on the success of any long-term reclamation process. These discussions haven't really yet happened for the Pebble project, so I'm not really sure what options they've got on the table with respect to the long-term reclamation process that they're going through. So I can't really say anything more about that at this time.
Okay. Thank you.
Jeremy, do you have another comment?
Yeah, sure. There's another sort of follow-up. I do feel that there is a gap in the study that's been done so far, and you mentioned it, and that's that no analysis has been done of sulfide-rich tailings. That seems to me to be the most likely problem material. The waste rock piles are going to have pretty low sulfide contents and may generate some acid drainage at some point. But normally the biggest risk from these types of deposits is, as we've been alluding to yesterday as well, the pyrite, which is a waste product, so nobody makes money off of pyrite. As I understand it, some of the ore in this deposit, the pyrite is associated with gold. So the pyrite may initially be treated in the ore stream, but then the gold is going to be separated from that pyrite by some undisclosed process or undescribed process at this point. And ultimately that pyrite is going to be going out into the waste in the tailings somewhere. So as I understand it, the study so far has only looked at sulfide-poor tailings, which are probably not a very significant risk. But if there is a section of the tailings ponds or a separate tailings pond which contains pyrite-rich tails, that would seem to be a very different beast. That's going to need much more attention in dealing with that in the long term. But I don't see that that's really been addressed here at all, that possibility, that apparently inevitable possibility that there is going to be some material like that.
Yeah, I agree that the data set to date doesn't include data that's pertinent to pyrite-rich tails, but those kinds of tailings products have been made available to us recently and have been submitted to the program. So, you know, in the fullness of time, the data from characterizing those materials will become available, and we would incorporate understandings from those data in kind of long-term planning.
So again, I mean, talking into the future, are there examples from other mines where people have successfully contained that type of tailings material effectively in perpetuity, not for 10 years or 100 years, but basically lock that stuff up and it's never going to pose a risk?
There are instances of sulfide-rich tailings in long-term facilities. I mean, actually, tailings in some respects, due to their very fine-grained nature, are in some ways easier to manage than a very coarse-grained heterogeneous waste rock heap, because by its very fine-grained nature, it's much more likely to have a high water content, to be close to saturation, and it's much easier to keep it saturated as opposed to a waste rock dump. And so the geochemical conditions in a tailings facility can generally be managed to minimize oxidation rates. So often in a tailings facility, the actively oxidizing zone within that tailings facility could be quite thin and very near the surface of the tailings. Yes, it's a long-term issue. It has long-term potential, but whether that potential would ever be realized depends on, how that material's managed and what containment strategies are put into place.
Right. I mean, I think that's a critical point, and the concern is that most of the most disastrous spills from mine sites have been tailings dams spills, breaches of tailings dams, leakages, whatever. It's very rarely that waste rock piles cause sort of wide-scale disasters. They might leak a little bit of acid perpetually, but the real risks of a tailings dam spill, is a tailings issue. So it really comes down to the integrity of the tailings dam itself, how it's built, and my understanding, talking to people who build tailings dams these days, is that they essentially design tailings dams to be stable for eternity. You used to talk about building tailings dams, for 20 years or the 100-year storm, but the industry standard now is to build them as though they're going to be there forever. And I think one has to look at it from that point of view. Because it's really not good enough to think, it's going to be good for 100 years, but then we're not going to worry about it because people are still going to be living here and salmon are still going to be in the rivers. So I think every time we look at this kind of stuff and talk about time, to me the time really is irrelevant unless you're literally saying this thing's going to be stable forever. If there is some time frame under which it might become acid generating or it might start to leak, then I think a red flag goes up there, and you go back to the drawing board to redesign it so that there never is, or at least within the bounds of realistic probability, there never is a chance that it's going to that's going to be a problem. Would that be a fair assessment of engineering practice today?
Yeah, I believe so. I mean, you're kind of taking me outside of my field of expertise here, but there was a bit of discussion of this yesterday, the kind of long-term stability of dams and the ways that different dam walls are constructed and what implications that has to the long-term stability. So some of the discussion yesterday is very pertinent to that point.
Anything else from the panel before we go to the public discussion? Well, thank you very much, Pat. So now we open it up to the audience for questions. We have the panelists and Claire, and we also have a few that have come in via email, so we may take turns with those. And again, if you step up to the microphone, speak into the microphone, and introduce yourself and who you're affiliated with, if you're affiliated with someone.
Yes, my name's Steve Burrell. I'm an independent consultant. Is it possible to bring Tom's slide up there that showed the particular line where he'd added the colorations on
it? Is this the one you're interested in?
Let's see. There was another one, wasn't there? That one right there. What the PAG material, given just my rough estimate is that we're talking a sulfide content of definitely less than 20%, maybe even in the 5% range total sulfides. And so, am I correct in saying that 5% of the mass of the rock would fit into the PAG category and 95% into the non-PAG?
I mean, this is, well, maybe I should let you answer, but
Please
you're
speak
basically
into the microphone.
Sorry, you're basing that on, I guess, the sampling density and the number of sampling points that fall into the different categories on that diagram?
No, I'm just basing it on the amount of sulfur that we saw yesterday in samples. Do we know what the percent of sulfur in the entire deposit is?
I showed some frequency plots. I don't know if you remember that showed the distribution of sulfur according to the exploration drill hole database, and that showed that there was quite a variable distribution of sulfur, and the range of sulfur contents was influenced by the rock type, whether it was the tertiary or the pre-tertiary. So I guess the density of sulfur varies through the deposit.
I understand, but if you looked at the entire deposit in aggregate, what's your best estimate of the amount of sulfur material there, the amount of sulfides that are within the deposit?
Gosh, well, maybe I could throw that over to one of the pebble geologists, actually, because that's partly a question of resource size.
Well, and the point being on Tom's graph, my estimate from looking at it is it's definitely somewhere less than 20% would be in the right-hand side of that graph, and so I'm just saying a large portion of that material is going to be non-acid generating material, it would appear, right there off that. And not based on those samples at all, but based on the overall deposit. Is that
the problem? The problem in thinking about that is you can't just look at a sulfur content analysis for the whole deposit and then decide how much of the material will be acid generated and how much won't. It really depends on individual, discrete samples throughout the pit volume.
I agree, but there is going to be an average.
There is.
Once you've discreted all of the samples, there is going to be an average, and that's my basic question.
That's true, but that gets to my point about heterogeneity in these piles. So we can't really treat these things using the average numbers because they're not homogeneous.
No, but for the general public to be able to put it in some kind of perspective, let's say they're moving 1 million tons of rock. Out of that 1 million tons of rock, there's a small portion that is potentially acid generating.
Right. Well, let's go to the previous slide if we could, just for a minute. So these are for the rock.
Okay.
Right? The one that we looked at previously was for tailings. So this is all the pre-tertiary rock from the east zone on the right and the west zone on the left. And I don't know how many samples are represented here, but if we look at them, the ones in the red zone are the samples from each of the zones that suggest that they should be acid generating.
Yeah.
So you can maybe look at the distribution of points above and below the blue and say maybe 10% not, maybe 80% yes, and 10% in the undecided zone. But that's perhaps a better way to look at this based on the distributions here.
Okay. Let me ask another question regarding the static test versus the kinetic. It is not the static test where you're flushing that thing continuously. Is that not going to give the worst case scenario you'd ever expect to see? You have a finely ground material.
I think
well
you're talking
exposed.
about the kinetic test, are you, where you're flushing it progressively? That would be, well, the humidity cell test that I showed.
Yes.
Yeah, I mean, yeah, I agree. I mean,
Okay.
it's also known as an accelerated weathering test because it's deliberately designed to accelerate the rates of reaction so that they're readily measured, in a laboratory time scale.
And so I guess what I'm saying is, can you then say that is likely the very worst situation that could ever exist?
Well, I would like to be able to say that, but I prefer not to be so definitive about it because as I mentioned, there are other variables like temperature and reaction rates would increase at elevated temperatures, and if a waste rock heap were to heat up, for instance, there is the potential that even in a waste rock environment, the rates could be accelerated. Whether as much as you would see in the humidity cell test, that's another question.
I'd just make a comment on that. I think Claire's caution is well warranted. There are deposits around the world that are in skarn settings, for example, where, if you take discrete samples and you put them in these accelerated weathering tests, you may never see, because there's a large excess of neutralization potential. In these tests, you may never see acidification. But then you go in the field after the deposits are developed and you find seeps that are pH 3. So it definitely occurs. Yeah.
Good, thanks.
Thank you. I think we'll have a question from the email here.
Yeah, this email that came in from Ann Mace with Stratus Consulting, and she has 3 questions for Claire. And I'll just state them one at a time so you can address them one at a time.
Okay.
The first one is, how will the information on time to onset potentially be used in management of mined materials based on your experience from other sites?
I guess one of the ways in which it might be used is in the context of ore stockpiles. If an ore stockpile, if there's a plan for that stockpile to be hanging around for a few years before processing, there needs to be some understanding of whether that stockpile would go acid during that period of time, and therefore whether stockpile management strategies need to be put into place to mitigate against impacts due to those kinds of questions. So that's one way in which that information can be useful. Also, there are instances where you could envisage that waste rock needed to be stored in one location before it reached its final engineered closure location, and again there needs to be some understanding of its behaviour during that time period before final engineered management strategies are completed.
Okay. The next question is, why do you think there is not a good relationship between NPAP ratio and final pH in the humidity cell tests? What are the implications for techniques that might be used in the field for estimating whether material is PAG or non-PAG?
The final pH in the humidity cell test is basically a function of whether or not that's, in the case of a PAG-classed material that's in that test, it's really a function of whether the neutralizing potential in that test has been consumed or not. It's perfectly possible that a test might run for many, many decades before the neutralizing potential is consumed. So clearly the pH would remain neutral for decades until acid onset. And certainly in our test program, there are several PAG-class samples that have yet or did not go acid during the time period that the test was run. And based on our calculations, we basically estimated that it could be decades before the test would be expected to go acid, and at some points you need to decide whether or not there's value in continuing that test or not. There are some tests in the program that are continuing, that are in that kind of period of lag time before acid conditions develop.
And the last question, which is kind of a follow-up to some of the previous discussion, you use calcium and magnesium concentrations to estimate the site-specific criterion for identifying PAG rocks and come up with a value of 1.6 for both pre-tertiary and tertiary rocks. Do you know what minerals the calcium and magnesium are contained in? Do you have enough pre-tertiary humidity cell samples with NPAP ratios greater than 1.6 to evaluate the usefulness of the site-specific criterion?
I believe that the calcium and magnesium are coming from calcium and magnesium carbonates, so calcite and dolomite. So that answers the first part.
So hydrothermal dolomite has been identified.
There is dolomite. It's not as widespread as calcite. So calcite's present. Well, I say widespread. It's present in some of the alteration cements. The NPAP critical ratio is not actually a function of the overall NPAP ratio of the sample. It's actually a function of the relative rates at which the NP and the AP are being consumed. So I don't think it matters that the pre-tertiary data set didn't include samples with a high NPAP ratio. In fact, there are very few pre-tertiary samples that have a high NPAP ratio. Most of those material types are PAG, so it's more a question of the relative rates at which the different reactive components of the samples are consumed.
Thank you. Are there any panel members who'd like to add any comments to that discussion?
Well, I just re-emphasize that this value of 1.6, I think, requires some additional thought and consideration of error bounds. This definition of an critical NPAP ratio and relating to the last question could also be affected by the time scale of the humidity tests. So that's also something that could be important to consider in using that method to define that critical ratio.
By that, do you mean you expect that ratio to change as the test progresses?
Well, in this case, if the pre-tertiary rocks all have NPRs less than 1 for the most part,
Mm-hmm.
and then you do the humidity cell tests and you reach a steady state, and that tells you that you have a critical ratio of 1.6, and it seems that you haven't conducted the tests to the point where all the NP is exhausted and you still have some AP. So,
as soon as the NP is exhausted, the test goes acid, and that critical ratio no longer applies. I mean, you've gone beyond the point at which it applies. All the data that I showed on that diagram was from tests that were still running at neutral pH, so therefore the neutralization mechanism was still taking place.
but it will become acidic at some point. Like
Some of those samples, yes, will definitely become acidic.
That's right. Yeah.
Go ahead, Jeremy.
Yeah, I guess sort of continuing with this trend of time, and I don't want to sort of feed you your lines, but I mean there are engineering solutions to dealing with acid-generating materials. Perhaps it would be worthwhile to actually describe one or two of the options that are available, that are out there for actually dealing with this stuff, because it does seem as though at some point in time we're going to be dealing with some acid mine drainage from either the tailings or the waste piles. So what strategies are there for actually dealing with that? Because as I understand it, there are quite standard mechanisms either for capturing that type of material. Some cases you can actually use it as kind of a leach process and actually recover metals. Or the other mechanism might be to import carbonate rocks to act as a long-term buffer for that acidity. So it might be interesting for people to hear what are some of the known options for actually dealing with acid-generating materials.
Okay. Well, I mean, you mentioned some of them. One method is incorporating some sort of containment, engineered containment to the waste material, and that's the kind of solution that's generally adopted for tailings. Tailings are placed in an engineered facility. Seepage from any seepage derived from the tailings is collected. Either never leaves the facility or it's collected and treated. So basically those materials are isolated from the general environment, and that's a solution that I guess prevents that particular material having long-term impacts on the wider environment. Waste rock's a little bit more variable in terms of the options that are looked at. I mean, containment is an option in the same way that it's an option for tailings, theoretically. But in practice, generally, waste rock dumps are managed in such a way that the reaction rates are minimised where as much as is practicable, thereby minimising the rate at which potential contaminants might leave or seep from that waste rock dump. And I guess the focus can often be on treatment technologies, collection and treatment of any seepage that might come from those materials. Another possible option that you alluded to there was blending or incorporation of limestone in the design of the waste rock dump, so that basically what you do is you introduce additional neutralising potential to the waste rock dump to try and influence the composition such that acid conditions do not develop in that waste rock dump. So there's a range of different options, and I don't know which are going to be explored in the context of this project.
I have a question which you may have answered, I may have missed, but I don't recall it. You've done these humidity cell tests longer than normally required, and I'm curious to know if they're still ongoing. Do you have tests ongoing, and how are you going to keep them going for quite a while?
We do, at this point in time, there are still some 30 tests ongoing. The longest running test is probably up to about 7 years now. So we have a 7-year-long data set for some of the samples.
Very good. Are there any more questions from the audience? Please, step up. Yeah.
My name is Paul Frost, and I'm from Togiak. And started commercial fishing in 1969, and I'm still commercial fishing. I guess the picture I'm trying to get is how is this mine? Okay, you're doing all these studies, and are they going to just like dig a big hole in the ground? Is that what they're going to do? And then they're going to put they're going to pile all this stuff up and then wash it with some kind of chemicals to separate the ore. I mean, how are they going to get the gold and the minerals, the money that they want to make, separated from all of the dirt? And how is making a big hole there, taking off the moss and all of the grass, and exposing that area? How is the sun, the weather, the sun, and the rain that we have, the tremendous amount of rain out there, how is that going to, how are they going to mitigate the poison from going into, we have river systems on top of the land, but we also have river systems under the water. I mean, there's water, it's all connected. It's like the it's like in your body, all your veins. I mean, it's all connected. And it goes a long ways. So if by chance, poison or this chemicals get introduced into this fragile ecosystem that we live on over there, I just can't, I'm having a hard time envisioning how, I hear you talking about, these PAGs and NAGs and you're going to, but I really am thankful for the studies. It's just at some point you're not going to be out there watching over and making sure that this is done. It's going to be some construction guy like me that's going to be running that 966 that's going to say, should I put this pile here or over here? And the boss is having coffee. And you get the picture. And in the end, they start out doing the right things, because I've been in dirt work my whole life, as well as fishing. And it starts out fine, but boy, when your timeline's running out and you need to make money, you're going to just move on. So how are we going to contain all of this? Are they going to put a big piece of 6 mil visqueen? Are they going to cover? Are they going to dig a big hole and then put this plastic underneath there, and then they're going to carefully put the first layer in so it doesn't puncture the visqueen, and then once you have that layer on, then we're going to dump the poisonous stuff in there and then sprinkle lime over it and then sort of mitigate? Is that what we're talking about here? How are we going to That's what I'm trying to. I'm hearing what you're saying, and I understand most of it. I'm just trying to figure out how this is all, what kind of so I can tell people when I go back that, oh, this is what they said, and this is how it's going to work, and these are the studies. I just don't have this picture. I have to see a picture.
I sympathise completely. I mean, it's a difficult picture to get, and I guess I should make the point that the studies that we've been presenting here are baseline studies to try and get an understanding of how the materials behave, and basically the understanding that we get will go into selecting management strategies or engineering strategies. Now, to get to your question was like, when you come to implement those strategies, how are you going to know that they're implemented properly, efficiently? How confident can you be that they're going to work? Those are really difficult questions to answer, and I guess as the project designs evolve, the onus would be on Pebble to put into place strategies, management strategies, to try and ensure that whatever management strategies they decide upon are implemented effectively. So I don't know if that helps or not.
Jeremy, do you have something to add?
Well, if I may, perhaps I could give a kind of a very brief description of the mining process. To answer your very first question, because we talk about tailings and waste rock and so forth, but it's not immediately obvious what it is exactly we're talking about. Fundamentally, the deposit is a volume of rock which contains metals of economic value. But that volume of rock is somewhere below the surface, and to get at it, you have to move a lot of other stuff. A lot of that will be waste rock. It contains uneconomic values of material. So if you take the mine as ultimately being some sort of big conical pit, a significant percentage of the actual rock that you moved out of that pit is of non-economic value. It's what we call waste rock, and that's the stuff which goes out on the waste piles. Now, the problem with that rock is that although it might not be economic, it might not have economic values of copper and gold, it almost certainly has, or some of it, certainly the pre-tertiary stuff, has quite a bit of pyrite in it. And that's the worrying component that we've been talking about here, because it's the pyrite that can generate acid. So it might be waste rock, but it's still carrying some pyrite and can potentially generate acid. So the waste piles that we were talking about, the reason that they're a problem is because of some of the pyrite in that material, and that needs to be managed. The ore, the mineralized stuff, which is what the company wants, that's processed very differently. That's typically, and again, it depends on the mine design, but from what I'm hearing here, it's going to be pretty standard, that you take that rock and you crush it to a very fine grain size, sand or even finer, to the point that you can separate the economically valuable sulfide minerals like chalcopyrite, the main copper mineral. You can separate that stuff from the rest of the rock, which is usually minerals like quartz, feldspars of no economic value. So what you end up with is a crushed material, finely crushed material. You can separate the valuable sulfides from that, usually by a method they call flotation, which separates the sulfides as a froth and you skim it off. And the rest of the waste material, which is now very fine-grained, goes out into the tailings facility. So that's called tailings. Now, in a typical ore, porphyry-type ore, you extract most of the sulfide because that's where your metal value is. So the tailings will probably be fairly low sulfide, and that was what was illustrated on the diagram that we saw, that much of the tailings are actually non-acid generating because you've actually taken the sulfides out because that's where the money is. The concern, though, is that the pyrite is still in that system and is still considered a waste. So you try and extract the chalcopyrite with the copper, the molybdenite with the molybdenum. Now, some of the pyrite has gold, and as I understand it, they will be trying to extract that gold from the pyrite, but ultimately the pyrite is going to go into the waste stream in some place, and that's what we were talking about this morning, how much of that tailings material will be pyrite rich. And there is certainly a chance that a significant stream will be high pyrite. That'll be the stuff that they extracted the gold from. And so far we haven't seen tests done on that potentially high pyrite material. So that's what we call tailings. Some of it may be low sulfide, but some of it may actually have significant sulfide concentrations. Now that stuff is traditionally put into a kind of like a pond-like facility, which may have a plastic lining, as you described. More commonly, it will have some kind of impermeable lining, such as a clay, some kind of material which reduces seepage. So depending on the design, you certainly design it so that you don't have leakage out of the bottom of this thing. And if you're going to design it, and as we heard earlier, you can design tailings dams so they're permanently covered with water. They're called tailings ponds. And the idea there is that the water prevents oxygen from the atmosphere getting into that stuff and oxidizing it. The problem you have there is you have to make sure that that thing remains covered with water in perpetuity. And some of the, as I mentioned earlier, some of the tailings dams failures that we've seen around the world, and Canada has a whole bunch of them up north, tailings facilities that were built years ago with no real controls. It's fine when the water's there, but you get a beaver in there which sort of undermines the front of the dam, and that happens. And the water escapes from the top of the dam, then you have a very serious problem, because then that thing goes into kind of a runaway oxidation process, and you get very extreme acid generation. So what I think we're hearing is that today you would not build a tailings dam in that way. You would build a tailings dam so that you were sure that it was going to maintain its integrity for effectively in perpetuity. That would be the design objective, and that's certainly the standards that the most engineering firms would use when they're designing a tailings facility. So yes, you're going to end up with a great big hole in the ground. You're going to end up with piles of low-grade rock, which, as we've heard, have the potential to generate some acid at some point. There are ways of managing that. And then you're also going to have these tailings impoundments, which I think probably are the ones that need to be watched most clearly, because they do have the potential for major problems.
I'd like to thank the last person who came up and asked that question. This is the kind of question that can help all of you who don't have the technical background to understand more about what's going on. And that's what we're here for, to try and help you understand not only all the studies, but sort of what might go on at this proposed mine site, and how it would work. And, you know, have they done all the kind of tests and studies that are needed in the baseline report. So I encourage any of you who are still struggling, there's a lot of technical stuff here, and anybody who's struggling with that now, it's a good time to ask a question. Please, go ahead.
So, Milo Atkinson with the University of Alaska. You gave a good context to my question, because I understood the solution to a lot of these potential problems was submerging stuff underwater in perpetuity. And what I didn't understand is I thought that you showed that some of these subaqueous tests, you had some samples that generated acid and liberated minerals. And I guess I'm wondering about the mechanisms by which that happens, and then what that means for what might happen in tailings piles or in submerged rock in a pit, for example.
Yeah, I did show data that from a subaqueous column that was generating acidic leachate. Now, that particular sample that was in that column had already gone acid before it went into the column, and basically what the data were showing was that it continued to release acidic leachate even under the subaqueous conditions. So if the material has already consumed any neutralizing capacity while it was exposed and has accumulated acidic reaction products, then it'll take some time after submergence before those acidic products would be washed out of the sample. And it's important, I guess, to differentiate between material that has not yet gone acid. If you manage to submerge that quickly before it's accumulated any acidic products, then you've prevented the further oxidation of the material and prevented the likelihood of acid onset. But if the material has already accumulated acidic products, there will be some period of time, even under subaqueous conditions, where acid conditions are possible.
But eventually, if you had that sort of phenomenon happening and it was submerged, eventually it would stop releasing.
That would be the hypothesis, but clearly those two tests that I showed have been going on for some period of time and are still giving acid leachates. So we're going to have to spend some time looking at that data and interpreting what exactly is the source of the acidity and verifying that acidity formed prior to the subaqueous test.
Thanks.
Okay.
If I can just add to that, I don't know if that's working. I was curious about those data as well, and oxygen has a finite solubility in water. I was wondering if you looked at whether or not just diffusive replenishment of oxygen could account for the acidification that you were noting?
Well, certainly those columns, if you remember, there was a column of water that was sitting above the actual sample. That water is oxygenated water. There's no attempt on our part to exclude oxygen from that water. So there is some finite amount of oxygen supplied to the sample. But I guess my perception was that the rate of supply would be so slow that further, new oxidation, for want of a better expression, would not be taking place, and that the acid products would have leached out. So, that's something I need to revisit and examine more closely.
We have another question from the audience, please.
Thank you. My name is Donnie Flegel, and I work for Weetabix Limited. It represents 5 villages in the Bristol Bay area. And I don't know if this is a real question, but something that I was thinking of, because we take a look at these plans and we take a look at, the worst case scenarios based on our own imaginations. And if we're going to do that, is there any way that some of this waste stream can be reused for some type of economic opportunity? That's a question I have. And just a comment, I'd like to thank the scientists that have come and recognize Rick Parkin here. I enjoyed the peer review panel that came up earlier in August, and I personally learned a lot. I know it's very hard to separate all of you and your peer review panel from folks that have hired you or commissioned you to do the work, but I do want to thank you.
Go ahead, Claire.
Okay. Well, I don't really know that I can answer your question very satisfactorily. I mean, I guess really where you're coming from is, is it possible to simply remove all those sulfide-bearing waste forms from the site, full stop, by in some way processing them to remove the sulfur, perhaps sell it on, I don't know. I think it'll all come back to whether or not it's economically feasible to try and go down that road. There's certainly options on the table about what their economic cut-off grade might be. If they were only looking at economic benefit, they might set that cut-off grade at a particular value. But if they were also looking at environmental benefit, they might deliberately make the cut-off grade lower so that they actually process a greater volume of the sulfide-bearing material than would otherwise be the case. So, there are those kinds of questions are being asked, but within certain constraints. And I probably can't say anything more on that. I don't know if any of the Pebble people here might want to comment.
Anybody from Pebble want to say anything?
I'm John Shively with Pebble. I think in general you're right. The volume is too great. And the example you gave of cutoff grade is something we're discussing The whole issue with pyrite, there are options that's come up. I mean, part is you don't do anything with pyrite and you separate it out in the tailings in an area. You could process the pyrite there, as you indicated, or there's also a possibility that we might be able to take all the pyrite and have it processed someplace else. So all of those things are things that are under consideration. But for the large volume of tailings and waste rock, for the most part, there probably is not a viable economic market for those things.
Yeah, I might just add to that that's the problem. I personally believe that every bit of, quote, waste material from a large mining operation could be used for something, and the reason it's not used is not economic. Just lose money on it. But this is an area where there needs to be more thought, more innovation, and I see that happening in some places. So we are moving in that direction, and hopefully more of it will be seen in the future. Next.
My name is Sam Snyder. I work for the Alaska Conservation Foundation. Twofold question. And the first gets to actually two now comments about worst case scenarios, whether it's in the humidity cell tests, if that's giving the worst case scenario. Given Tom's point on the precautionary principle, just simply isn't that what we should be designing for as worst case scenario, particularly in a place this wet, this windy, and where the conditions are still so unknown. And I think Tom pointed out a lot of those the uncertainties with these tests in the lab as opposed to the field. And then a second follow-up to that, if copper leaches underwater and it creates under acidic conditions, it leaches, and it also leaches underwater, and selenium and so forth leach under a variety of conditions. Doesn't this mean that really success in containing potential acid mine drainage, tailings facilities management depends upon water management working perfectly? And so this goes to the mitigation technology question. Again, are there examples of other large mines of this size, of this type, in this type of place, where we have examples of that working on a long time frame that can provide that sort of confidence in the historical record of the mining community? And I'm just going to sort of book into with that and say, don't give me the Fraser River as the example, because we know that fishery's a mess. Thanks.
I don't really know how to answer that. There are, as I mentioned, there are analogous mine sites in operation, and my colleague has actually done a review of experiences at those mine sites, both positive and negative. I think in terms of positive experiences, they do tend to be more associated with recent mines, in other words, mines that have been operated on the basis of current best practice as opposed to what was best practice many, many decades ago. And almost by definition, because those are recent mines, the data that's been generated that could be used to measure the success is relatively recent data, and so therefore we haven't got a data set at the moment where we can test the long-term performance of those kinds of criteria, simply because that data hasn't yet been collected. So it's a question that's impossible to answer, really, but you know, the intent is there.
I would ask Jeremy or Tom if they might have something to add to that, because even though the mine may not be the same, well, the mineral deposit may not be quite the same, there are places in Canada with very large, extensive tailings that have been held subaqueous as a technique of preventing acid drainage. And I haven't kept up on how well that's working, but some of those have been around for, I don't know, a couple decades at least. Isn't that right?
Yeah, I think mines that were built over the last 20 or perhaps 30 years have been built with tailings dam construction techniques that are designed to last, if not in perpetuity, but to withstand the decadal storm or the 100-year storm. Whereas dams that were built 40 or 50 years ago, they were just built long enough for the owners to get out of town when they were when they were finished, and that is a huge problem in northern Canada. There's thousands of abandoned mine sites in northern Canada that were built, in the mid 1900s, where these sorts of controls on long-term storage just weren't a consideration. People built them long enough, as I say, for the mine to last, and then they walked away and threw away the key. And now the taxpayer, of course, is picking up the bill for remediating those sites. And that's a major issue, but it is a historical one, and it's one that certainly the modern mining industry is taking very seriously. And literally, you talk to tailings dams designers, they talk about designing their dams to last in perpetuity. Whether they actually do, we don't know, because we haven't had perpetuity to watch. But certainly there's very few cases of relatively recent tailings dams which were constructed to high specs. There are very few instances where there have been any problems. I'm not going to say never, I never say never, but I'm not aware of any that recent tailings dams that have been built to high spec that are showing any signs of problems. Well, the water... Yes, exactly. I mean, the question was, what about water management? And I mean, I think that is the big question. If you are maintaining, for example, a tailings facility which is required to be covered with water to stop it going acidic, then you're saying that you have to keep it covered with water in perpetuity. So the mine is going to have a finite lifetime. What happens when the mine locks up and walks away? There are examples where there's ongoing remediation being paid for by companies long after they've closed the mine. Many mine plans require that. But, again, you can project that out a few decades, but it's very difficult for us to predict whether that company is going to be around in 50 years' time, 100 years' time. Are people still going to be managing the water situation there? So, I prefer to see facilities like this which are engineered as standalone things which don't need maintenance. They're designed so they don't need to be maintained, and that's one of the reasons for using things like carbonates as a natural buffer for pH. You build your containment facility out of that stuff so that it actually contains acid that might be generated in perpetuity. If you're going to rely on sort of maintaining a water level and so forth, I think there's a much greater risk of at some point something going wrong, and you're going to lose that water or something like that.
Yeah, I might just mention that probably the most common water management technique that's used these days for these acid drainage situations is to treat it with an acid neutralization plant. That is, you set up a chemical plant that adds lime and neutralizes the water, and then you have sludge disposal, and hopefully in a safe place. And the problem with that is that the seepage or the discharge of bad quality water from mines can go for a very long time, hundreds to thousands of years. And so those chemical plants aren't going to be there that long. And we're still, and for many of those sites, usually abandoned mine sites, we have the problem of what are we going to do as a walkaway solution, and there really has been very few of those, if any. Next question, please.
If I can, just for a second, comment on the same issues. Tailings, it's an issue of integrity of the dam, and I don't think it's reasonable. I think we have to be cautious when we say designing for infinite time. So that's a real issue. I think design aspirations might go there, but practicality is not necessarily there. So for tailings, saturation by water is a very good solution. If you can maintain that for a long time, that's great. In Canada, there have been some examples around the world of subaqueous disposal in natural freshwater systems and in marine systems. And that's pretty offensive to a lot of people, because you say you're going to dump those tailings in that beautiful lake, and you have to understand that reaction. But if you want to think into the long term, that is probably the most stable setting, because it's a natural basin, and you don't have to worry about dams and whatnot. So that's one option, and you can argue about the pros and cons and so on, but the tailings have to remain saturated. If you can't do that, if you have dam failures, then you've got a problem, a big problem. As far as waste rock goes, you're dead on. It's a water management issue because you can cover them, you can add carbonate, you can do all sorts of mitigating measures. You're never going to stop that bleed of if there's oxidation, if they're exposed subaerially and the water table is low, then you're going to get some leachate that is, for these types of materials, likely going to be acid generating and metal containing. So you've got to maintain some sort of facility to look after that water. It's water management. And in Canada, we get closures on mine sites, and we call it perpetual treatment. And as Kirk says, it's line treatment plants, and companies commit to perpetual treatment. And, what does that really mean? Time will tell. Right.
Okay, we're running out of time, so we'll just take 2 more questions. Please keep them focused.
Okay, Phil North, Environmental Protection Agency. And I'm wondering if you could touch a little more or discuss a little more on the mine workings themselves, the pit, or if it were perhaps an underground mine, and the implications of the data for there. You've touched on it a little bit, but it would be interesting to hear what the longer-term implications are.
Okay, I guess I can't really say too much about the longer term implications until we've kind of gone through the process of scaling up from our laboratory test work to the kinds of scenarios that we are talking about in the field. In terms of a pit wall, for instance, we would need to know exactly what the composition of the pit wall is, and that sort of information would be available once the mine plan's finalised, because they'll have a model of where the pit volume actually resides, where it's located, and there'll be some way of mapping, if you like, the composition of the pit wall surface. And basically what we would do then is have a look at what proportion of the pit wall surface was sulfide bearing, and again there are engineering options here to perhaps manipulate the final pit volume so that you minimize the amount of exposed sulfide mineralogy. So again, there are questions there that feed into the mine planning evolution. But anyway, having determined the proportion of the wall rock that's sulfide bearing, we then need to find some way of applying a rate of oxidation of that wall rock versus the rate at which rain, for instance, is rinsing that pit wall surface. And that's going to give you some degree of quantification of a source term, we might call it, so a contaminant source term that's represented by that pit wall. And that needs to be put into the context of an overall kind of site water balance, like what volume of contaminated water does that runoff actually represent, and when you mix that in with all the other water sources at the site, how important does that particular contaminant source become compared to other potential contaminant sources? And these are all questions that would be addressed as we kind of go forward with the water quality predictions.
I wonder, are there analogous situations? The Berkeley pit in Montana is the famous, acid pit, and are there other examples where there's maybe they could be drawn as parallels?
There are bound to be some examples, perhaps in some of the Canadian porphyry examples that Steve has reviewed as part of the review. I'm afraid I'm not totally familiar with the detail of those sites and whether there were pit lakes or not, and whether those pit lakes were acidic. It's all going to be a matter of the quantity of acid that's being generated on the pit walls versus the amount of dilution of that acid by other water sources. So it'll all come back to the water balance, if you like, for the particular site in question. And for this, for a conceptual pit at Pebble, I don't really know what that water balance is, and therefore what the relative importances of the different sources of contaminants would be.
Thank you.
Do we have one more question?
Thank you. Philip Applecock Sr. from the Michigan River. On the waste rocks, when after they're in mines that are already in operation, the contaminants and acid is there, and you guys take them up and you guys put them in a pile, and you guys be able to drain them out and take the acid out, and in the reclamation, how many years you got to be able to use that rock to be able to put it in a reclaimed area that is not contaminant when you reclaim it and replant that area to as is. And the water in the mine that are already built, you got to be able to run that. After you take the gravel, you got to run it through and be able to put it in a system and be able to put some material in there to separate the gold from the precious minerals from the material, and you use some chemicals, and then you got acid, then you create another acid waste tailing is gravel. And the other question is on the water. You got it's contaminant water, and in order for you to be able to filter that water within a climate as Alaska, you got to be able to build something to be able to filter that water out. So when it comes out in the end, it got to be contaminant free, and I think that's the fear that. And you got to be able to, at least one more thing is, you guys say that lining lasts for many, many years. But you guys got to be able to see that, if a big, enormous, gigantic mine it's going to be built here, and you're looking at gravel waste that's going to be billions of tons, and you got water. You got to be able to put them someplace. How long will that lining last? And you're talking about a critical area. Thank you.
Claire?
I think the question was focused on, I guess, how confident we were that either the solid waste streams, the different kinds of solid wastes on the one hand, or contaminated waters on the other hand, how confident we were that those kinds of materials could be managed in the long term in such a way that the wider environment was protected. Is that fair? Is that what the...
Well, we're dealing with water that's cold, and in Alaska, the winter months are not 6 months long. Now they're eight months long, and in the 30s and 40s they were 9 months long. Climate change it down to 8 months long. They're not 6 months long. And on the water tailings, you got to be able to let that water go to a system before then you'll be able to come out contaminant free, and you could be able to at least put it back, and there'll be no contaminants in that lake, or will there still be contaminants as in the gravel tailings?
I think ultimately where you're going is what should be the performance criteria that the project can be judged on in terms of the local water quality, and I get those performance criteria. I believe have still to be agreed, decided upon. I can't comment on them myself. It's kind of outside of my area. The type of work that we've presented here was really, I guess, basic geochemical characterization work that's to be used to help understand long-term behaviours. But in terms of putting closure strategies into place and identifying the performance criteria that those strategies must meet, that's a process that I believe has yet to take place, but perhaps somebody from the Peril project can say something on that topic. Or maybe not. It's kind of outside scope, I think, of this particular discussion. Certainly it's not something I personally can talk to. Oh, we've got...
Yeah, well, I mean, I think Philip is concerned about a whole range of different issues, all of which you've talked about here, and all of which I think we're going to have to address as we develop the mine plan. Water treatment is pretty sophisticated these days, so testing to find out what we actually have to deal with, which is part of the work that's been done here, is essential to our understanding how we have to design the water treatment plant. The state has very high requirements for what we have to put, what we can put back into the environment, and we will have to meet those. And at least at this point, we're going to have to meet them long term. And how we fund that is an issue that will be developed during permitting. In terms of how things like waste pellets are going to operate over the long term, I think that's part of why we're doing some of this work. But those are issues, and what you do with some of that in the long run, whether you process it at the end, whether you put it back in the pit, all those issues are still things that need to be considered. But I mean, in the end, we have to design something that we believe does not allow things like acid and excessive minerals to get back into the ecosystem. That's the challenge. And I know some people think we're delaying producing a mine plan for all sorts of nefarious reasons, but this is a very complicated project, as we've seen, and so we're taking our time to try to get those answers right.
Thanks, John. Now we've reached almost the end of the first panel review on geology and geochemical characterization. We've left a little bit of time at the end just before lunch for our panelists to give about a 5-minute summary preliminary recommendation, basically to summarize the highlights of things they would recommend as a result of their review and evaluation. it be all right if we could change the order, maybe from this end to that end? Would that be a change of pace, maybe, and start with Larry?
Sounds good to me.
And actually, if Claire wants to join you're not going to have to be focused on this at all. So.
Get off the hot seat now, can I?
Thank you very much, too.
Yeah, I've got a few comments, few take-home points, if you will, from the past day and a half of observation and sort of questioning what's been going on. We've been tasked to review 5 years of a baseline study, but it's hard to just let it go at that and not think about the future and what might be coming along as the mine is developed. And so because of that, I've got some questions in my own mind that I've come up with that I'm going to repeat here, and we can sort of just ruminate over them a little bit. One of these is that, we've got the Usabelli coal mine up the road here that has been working for, over 40 years now. And they have a mine land reclamation effort that has been a pioneer for cold climates. And I know for a fact that in the beginning they just were throwing seeds out, hoping something would grow. But they've become very sophisticated in their reclamation work, and it's become a very successful effort. And I hope that the people at Pebble will take advantage of this expertise and see if a lot of that can't be transferred over to where they'll be working. Also, the NRCS in Palmer has established along the transatlantic or Trans-Alaska pipeline route a number of reference soil sites that they monitor and look at. And I'm sure that they would be interested in setting up similar reference soil site areas in the Pebble Prospect region if they were contacted. I know for a fact that there aren't any of reference sites out there right now. So it would be a matter of getting a hold of them and working with them to set up these sites. I think that would be worthwhile doing. Let's see, what else? Yeah, the work of Clark and Ping in the Chiswick Island area is one of the references that we have for soils of the region. There are also a couple of studies that I'd like to call your attention to that have occurred in the west of Tyonek in the Caps Coal Field area, and these are USGS open file reports dated in 1983, and they're 83-190 and 83-246, and these were these studies involved the characterization, not only the characterization of the soils, but also the geochemistry, and they'd be worth looking at least from a reclamation perspective. Yeah, the studies that were that were looking at soil basically were three that I could find. We had the small scale 1 to 1 million background and literature study that Greg talked about yesterday. And as far as I can tell, there wasn't a whole lot of integration between that one and the soils that were described in the vegetation study, and also which will be reviewed next week, I guess, and the soils that were characterized in the trace element methods section. But I think there needs to be a little bit more integration among these efforts to look at not only the geochemistry of the soils, but also the physical character of the soils. I've got a few more points, but I think I'll let it go at that at this point. And yeah, so if there are any questions, I'd be happy to answer those.
Okay, well, probably in the interest of time, we'll move on to Steve.
Okay, I'll give a brief review of some of my recommendations for particularly the seismology and the volcanology part of it. The first one, I think there's justification at this time to do a first-order probabilistic seismic hazard assessment. At the very minimum, you want to give the relative hazard for the various sources that have been identified, the subduction zone, the deeper slab events, the local ones, and then this idea of a floating event. For example, you could give a table that shows the distance to the source for each of the sources, the magnitude range, the recurrence rate, the likely shaking amplitude, the period, and then so you want to be able to quickly at a glance get the relative hazard from these different sources. Because the data are dynamic and readily available, we need to assure that there's dynamic data gathering capability. For example, the ability to update plots of earthquake occurrence and the relations on the web page, for example. Explicitly consider the effect of earthquakes on the transportation corridor, particularly the Bruin Bay Fault. The Iliamna deep cluster should be considered along with the as was one of the three sources in the relative hazard stated earlier. And with those data, then you can then determine the likely risk for the 30 to 35 year period during which the mine would be expected to be active. The soil conditions and the effect of overburden removal need to be explicitly considered. I think there needs to be explicit statements of the variance. One comment drifts a bit into some of the discussion today. I think I haven't heard it mentioned explicitly. We want to make sure that the shaking hazard is included in the tailings design. One can imagine a pile of loose rock and you shake it in a magnitude 8 earthquake 100 kilometers away. There would clearly be some kind of effect that needs to be considered. I think whether the Lake Clark Fault extends further to the southwest is still an open question, and we need to, at this point, clearly define the difference between the hazard, which appears to be low because of low activity, and the risk, which is high because it's the closest main fault to the activity. So one way to approach this would be to do a sensitivity analysis, do a comparison with the present known location of the Lake Clark Fault to see what the formal hazard is, and then extend it farther under the mine and repeat the analysis to determine what the effect is from that uncertainty. Okay, that's the seismic side. On the volcanic side, I think several of the volcanic centers to the west need to be explicitly considered. Katmai, Novarupta, which is one of the vents in the Katmai region, Aniakchak, and several of the other major peaks, explicitly put in information about the wind direction and speed, the wind rose diagrams, because a lengthy eruption there would dump a lot of ash, which would show up in the mine site and would be an ongoing concern. For example, you wouldn't be able to operate aircraft if there was a long-lasting eruption. Determine the size of the events and the frequency of occurrence. And those are my main recommendations at this time.
Steve, I had a question. Yesterday you mentioned the possibility of, or the suggestion of, a small seismic network associated looking at small movement potentially along the Lake Clark Fault extension. Are you still?
Yeah, okay, I'm fighting a little war with myself here. I mean, my comments that I gave so far were directed strictly at the study as it exists and the information we were asked to evaluate. Whether you extend that by adding a seismic network, yes, I would like to see that done. I think it would be a good idea. I'm not sure exactly where that fits into the current process. I will make sure that I contact some people and see whether this is feasible to do this. I think it would add, but it's not something that has been done yet, so it's not clear exactly where it fits in the present scheme.
All right, thanks.
I'll just make a few comments as well. Some of this will be similar to some of the remarks that Steve just made. With regard to the superficial geologic mapping that was done at the mine site, the work there is state-of-the-art. There are no real issues. The superficial geology appropriately and adequately characterized in great detail, and lots of other details associated with that work with regard to the glacial geologic history of the area. But with regard to similar detail in the transportation corridor part of the study area, I think more work could be done to better characterize the superficial geology and particularly the hazards associated with that transportation corridor. There are likely some slope stability issues, landslide, rockfall issues that need to be evaluated, and the 1 to 250 scale mapping of Detterman and Reed, although excellent at its time, is probably too small a scale to be used for an area like that. So I think some additional superficial geologic work in the transportation corridor area and in the Cook Inlet drainages would be warranted. Let's see. What else have I got here? I'd also agree that additional studies on the Lake Clark Fault are warranted. We want to know exactly where it goes to the southwest, when it was last active, how big earthquakes could possibly be on that fault. And just to reiterate, the glacial deposits that overlie the fault trace are thought to be roughly 12,000 to 10,000 years old, and they are not displaced in any way by the fault itself. So that's where the inference that there's no evidence of activity over that time frame comes from. Of course, that could be refined somewhat by studying those deposits in more detail and trying to get age estimates to pin that down even better. And then I would reiterate that the main volcanic hazards are likely to be ashfall, and as Steve mentioned, these eruptions may persist for weeks, months, and the effects of ash could be a persistent problem. It's probably not a deal breaker, but as we all know, those of you that have been around for some of the recent eruptions that we've had here in Alaska, air travel can be suspended for days, sometimes longer, and that could complicate some issues. And then before we let the subject of volcanology go, I think it's also important for us to bring to light other studies that may have some bearing on what we're trying to do here. And I just wanted to mention an event that happened at Chiganagak volcano, which is located just south of Pilot Point. Many volcanoes in Alaska have crater lakes in them. They have summit craters that fill with water. And if the volcanoes are active, they're going to be releasing sulfur gases, which when they react with water produce acids, sulfuric acids. The case of Chiganagak, that lake in the crater, was very acidic, and it breached catastrophically sometime between November of 2004 and May or April of 2005, and it produced a very large acidic flood that made its way into Mother Goose Lake. It was about 1 million cubic meters in volume, so it was a pretty substantial flow. The pH of Mother Goose Lake went from about neutral to in the 2 to 3 range right after the flood. And yeah, right. Needless to say, all of the aquatic habitat along the flood route and in the lake was destroyed. Fish were gone. There was no salmon run that year. But about 3 years later, the fish began to come back, and currently the area supports a pretty robust salmon run. So there are some natural nature performs experiments for us all the time, and we can learn a lot about the robustness of various systems by trying to learn from these sorts of events. My colleagues at AVO have published a couple of papers on this, and I can provide those references. But there is a big literature on acid lakes and volcanoes and their drainage, and they are somewhat of an analog to acid mine drainage. So I think it's important to try and pull in some of these studies, maybe from fields not directly germane to mining, that might shed some light on what we might expect in terms of impacts and recovery. And I think I'll just stop with that.
Okay, Tom?
Okay. I'm going to just restrict my comments to the data at hand. And, if there was a mine plan, then there perhaps would be a few more questions coming from me. But really, I guess my principal point is that we have to be careful with this issue of prediction. Prediction is dicey at the best of times. I think if we're using these kinetic tests to predict, say, the future onset of acidification in waste materials or water quality, then there's a tremendous amount of uncertainty. And I think we really have to acknowledge that, and perhaps, we could step back a little bit and say, okay, acid-base accounting works fairly well for identifying materials. Let's find a realistic threshold for the neutralization potential ratio. Let's make sure that there's some risk safety factor built into that, and perhaps, as Claire suggested, then some sort of program akin to grade control, whereby you use, say, rapid analyses for calcium versus sulfur, that could provide the density of data in time and space that really helps in terms of segregation. Because segregation of material, if it's going to be done, it has to be done with some confidence, because if you make those decisions, you move material that you think is non-acid generating, and at some point in the future it becomes acid generating, then you've got a real problem. So I think that issue of segregation is important. I think we have to find methods with confidence of doing it, and it deserves a lot of thought and consideration. And humidity cell tests, kinetic tests, and whatnot, I really don't honestly have that much confidence in those. And then the last thing is the business. In terms of the data at hand, I don't think we have enough data on the tailings disposal. And I think that's been acknowledged, the pyrite concentrate. There's really no data for that. We don't know the fractions of the pyrite concentrate relative to the bulk tailings. I think we probably know that it would be a net acid producer, but what we also don't know is how it's going to be treated. I mean, there's a whole range of ways of treating a pyrite concentrate, everything from pressure oxidation through to cyanidation, and we don't know which of those choices would ultimately be used, and they all have their own implications on the geochemistry of the system. So there's a lot more. There's a lot more to be done before all these questions can be answered. But I think at this point the work that has been done is good, and I certainly feel that way. But I do think that segregation is very important. We need to have a program for doing that with confidence, and I haven't seen that yet. So.
Okay, Jeremy.
Okay, so taking the baseline study at sort of face value and thinking about the pebble deposit and the location, to some extent it's an ideal deposit. It's the geographic location is fairly flat lying. You don't have risks of landslides and so forth around the actual deposit itself. The geochemistry of the deposit is fairly benign. There's not a major risk from elements like arsenic or mercury actually within the ore deposit itself. So compared to some porphyry projects that I visited around the world, this is actually a pretty easy task to engineer a good mine. The concern, of course, though, is when you step back a little bit and say, okay, well, where exactly are we? and you look at the mine in terms of its broader context, in terms of salmon fisheries and so on and so forth, then I think that simply focuses the challenge for the engineers to come up with a design which really will work. And I think amongst some of us, we've been talking about building in redundancies and fail-safes in terms of one's assurance about water management, tailings management, and so forth. Probably sort of one solution is not going to be enough. We're going to need to multiply the safeguards to really make sure that there never is a significant spill from this operation. I think that's probably a challenge the engineers are up to. Of course, it's always an economic consideration. At some point, the whole project becomes economically unfeasible. But I think today companies, when they're designing mines, they talk about planning for closure. And so I would like to see, as they develop the mine plan, starting from day one, and this is day one, we're looking at the baseline studies, but starting from day one, thinking about the environment that you're building this mine and how are you going to build it so that you can shut it down at the end of the day and it is not going to cause any risk to the environment for the foreseeable future. Of course, we acknowledge that in perpetuity is an unrealistic prospect, but within the scale of reasonable prediction to design a mine that will maintain its integrity after closure for as long as we can plan it. So the mine itself, I think, is a nice operation. It's a wonderful deposit, and I think engineering-wise, we certainly have the capability to design a good project here. So I'm pretty comfortable with what I see at this point. There's no huge red flag that in my mind says you should never dig up the turf here. But there are those longer-term issues that I think we need to build in right from the beginning. The transportation corridor, in fact, is where I have the greater concern about a possible risk in terms of a spillage. And we discussed that a little bit yesterday in terms of landslide risk along the transportation corridor, particularly along the north shore of Lake Iliamna, where the corridor appears, under current sort of routing designs, appears to run along the lake shore and at the foot of some pretty steep hills. We've heard a lot about seismic risk, volcanic risk, and so forth, and just general landslide risk from steep topography. A significant landslide which took out your transportation corridor and the 5 pipelines that have been talked about running up there to bring ore concentrate down to the coast and return water, oil and gas, you could have a significant spill if there was a landslide affecting that transportation corridor. And I didn't really see much in the baseline study that addressed that risk. So that's something that I think would need to be addressed. Yes, we're being told that there is no plan, but I think any plan is going to require some kind of pipeline. So even if we don't know exactly where it's going to run, I think we do need to evaluate the stability of that region and the risk and the way that one might mitigate the risk to the integrity of a pipeline like that. But so those would be my thoughts at this point.
Thank you. Just a couple of closing comments. First, this is the end now of our first panel review covering the geology and geochemical characterization. The presentation discussions you heard this morning is our bridge to the next panel review, which is on the hydrology. So we've heard about source materials and how reactive they are and the tests that were used to that, but that all has to be taken into the context of the water flow of the system. We have to know something about where the water is flowing and how fast and so forth. And so the next panel session starting after lunch will be on the hydrology. The other thing I'd like to say is that these 5 gentlemen here who have kindly provided their own time to come and review many pages of technical work should be applauded for their efforts, and I personally really appreciate the work that you guys have done to go through this stuff, review it, and ask some critical questions. Thank you.
Let's thank Kirk and Philip as well for their effort.